The inner workings of search algorithms, a developer's deep dive in the world of computer science. Search algorithms form the backbone of efficient data retrieval. These fundamental techniques power everything from web searches to database queries, making them essential knowledge for any serious programmer. Understanding different types of search algorithms reveals how we efficiently find information within complex datasets. This guide explores their inner mechanics, performance characteristics, and practical implementations across various domains. Fundamental principles of searching. At its core, searching involves locating a target value within a dataset. The efficiency of an algorithm depends largely on whether the data is sorted or unsorted, and what kind of access pattern is required. Unordered collections require brute force approaches that check every element until a match is found. Ordered structures enable more sophisticated methods that reduce average case complexity significantly. Data structure choice fundamentally shapes which search strategies are viable. Arrays allow random access but have fixed sizes, while linked lists offer flexibility at the cost of slower traversal. Time-space trade-offs become critical when choosing between linear and binary search approaches. Memory constraints often dictate the optimal solution for real-world applications. Linear search techniques. Linear search remains the simplest approach for finding elements in unsorted arrays. It sequentially checks each item until the target is located or the end is reached. This method has a worst-case time complexity of O(n), where n represents the number of elements in the collection. However, it performs well in best-case scenarios with early matches. Implementation simplicity requires only basic loop constructs without additional memory overhead. Adaptability works equally well on both primitive and complex data types. Guaranteed results will always return correct answers regardless of input size. Despite its limitations, linear search maintains relevance in small datasets or situations requiring frequent insertions/deletions. The algorithm shines particularly when dealing with dynamic data structures where maintaining order would be computationally expensive. Binary search fundamentals. Binary search revolutionized searching by leveraging ordered data to achieve logarithmic time complexity. This divide-and-conquer strategy repeatedly narrows down the search space. To use binary search effectively, the array must be sorted in ascending/descending order. Otherwise, the algorithm may produce incorrect results. The process works by comparing the target value with the middle element of the array. Based on comparison outcomes, it discards half the remaining elements. Space requirements remain constant as no additional storage is needed beyond the original array. Time complexity reduces dramatically to O log n in average cases. Applications span numerous fields including library systems, medical records management, and scientific computing where rapid lookups are crucial. Advanced variations of binary search. Variants of binary search address specific edge cases and optimize for particular application needs. One such variant handles duplicate values by returning the first/last occurrence index. Another variation finds the insertion point for new elements in a sorted array. This proves useful when maintaining ordered sequences dynamically. Some implementations include sentinel values to simplify boundary conditions, reducing the need for explicit range tracking during iterations. Careful handling of midpoint calculations prevents infinite loops in certain scenarios involving odd/even length arrays. Performance benchmarks show these optimized versions can be up to 30% faster than standard implementations under controlled testing environments. Tree-based search algorithms. Binary search trees introduce hierarchical organization to facilitate efficient searching operations. Each node stores a key-value pair along with pointers to child nodes. The tree structure allows for O(h) search times where h represents the height of the tree. In balanced trees, this translates to O log n, complexity similar to binary search. Insertion and deletion operations maintain tree properties by following specific rotation rules. This ensures continued viability for future searches. Self-balancing variants like AVL trees automatically adjust structure after modifications to prevent degeneration into linked list behavior. Real-world usage includes symbol tables in compilers, file system directory structures, and distributed databases requiring fast query responses. Hashing mechanisms in searching hash tables represent another paradigm shift by transforming keys into direct indices through hashing functions. This enables near-instantaneous lookup times. The ideal hash function distributes keys uniformly across the table to minimize collisions. When collisions occur, resolution strategies determine lookup efficiency. Collision resolution techniques include chaining, using linked lists, and open addressing, probing alternative slots. Both approaches affect overall performance metrics. Load factors play a critical role in determining when resizing becomes necessary to maintain acceptable operation speeds. Modern implementations combine perfect hashing with probing mechanisms to handle large-scale data processing demands. Depth-first versus breadth-first search graph traversal algorithms provide solutions for searching nonlinear data structures. Depth-first search, DFS, prioritizes exploring paths fully before backtracking. Breadth-first search, BFS, systematically examines all immediate neighbors before moving deeper into the graph hierarchy. This guarantees shortest path discovery in unweighted graphs. Memory consumption varies significantly between the two approaches due to differing queue implementation requirements. Use cases favor DFS for problems requiring exploration of complete branches, while BFS excels at finding minimal steps between points. Both algorithms demonstrate versatility across diverse applications ranging from puzzle solving to social network analysis. Heuristic search strategies when exact solutions aren't feasible. Heuristic-based approaches approximate optimal paths using informed guesses. These methods excel in complex problem spaces. Asterisk search combines uniform cost principles with heuristic estimates to prioritize promising directions. This makes it highly effective for route-finding applications. Evaluation functions determine priority queues ordering, guiding the algorithm towards potential goal states efficiently. Admissibility criteria ensure heuristics never overestimate actual costs, preserving optimality guarantees in many scenarios. Recent advancements integrate machine learning models to enhance heuristic accuracy for emerging AI-driven applications. Quantum search algorithms. Quantum computing introduces revolutionary paradigms through superposition and entanglement capabilities. Grover's algorithm exemplifies this potential. Grover's approach achieves quadratic speedup by exploiting quantum parallelism. It offers significant advantages for unstructured search problems. Complexity improvements transition from O(n) classical to O(n) quantum execution times, although hardware limitations persist currently. Potential applications span cryptography, optimization, and machine learning domains where traditional methods struggle with scale. Ongoing research aims to overcome decoherence challenges and realize practical implementations of these groundbreaking techniques. Comparative analysis of algorithm performance. Different search algorithms excel based on specific constraints and requirements. Comparing their complexities helps choose appropriate solutions. Best case scenario for linear search occurs when the target appears at the beginning of the array, yielding O(1) performance. Worst case analysis shows linear search degrades to O(n), while binary search remains stable at O(log(n). For sorted static data, binary search outperforms other methods consistently across varying input sizes. Hash table lookups typically operate at O(1), assuming minimal collision occurrences and adequate load factors. Practical considerations for real-world implementations. Choosing the right search algorithm requires evaluating several practical aspects beyond theoretical complexities. Real-world constraints influence decision-making processes. Data volatility affects algorithm selection. Frequently changing datasets might benefit from different approaches than static ones. Available resources, including memory footprint and computational power, impact feasibility assessments. Security considerations sometimes necessitate avoiding predictable patterns inherent in some deterministic algorithms. Interoperability with existing systems forms another critical factor in technology stack decisions. Emerging trends and future directions research continues pushing boundaries in search algorithm development. Several exciting trends indicate promising future trajectories. Approximate nearest neighbor algorithms gain traction for high-dimensional data analysis tasks where precision isn't paramount. Federated search frameworks enable collaborative querying without exposing raw data, enhancing privacy protections. Advancements in neuromorphic computing suggest novel architectures could revolutionize search methodologies entirely. Integration with blockchain technologies opens intriguing possibilities for decentralized information retrieval systems. Conclusion: mastering search algorithms equips developers with powerful tools for optimizing information retrieval across diverse computing landscapes. By understanding the strengths and weaknesses of different approaches, programmers can make informed choices tailored to specific project requirements.